Good morning, guys. This morning I'm going to talk to you about electronegativity and bond polarity. The elements have various properties that we've talked about: density, electrical conductivity. More recently, we talked about specific heat capacity. And they also have a property called electronegativity. And so let me define for you what this property is. If you could turn to your page in your packet where it says electronegativity, let's go ahead and define what that is. This is the ability or the tendency of an atom of an element to draw bonding electrons toward itself. Bonding electrons toward itself. Okay, so I want you to underline bonding electrons because that's really, really important. When you look at this this periodic table, the relative height of the columns of the elements here, it's sort of like a three-dimensional bar graph. The higher the column here, the more electronegative the element is. And the scale is kind of difficult to read, but basically as the color of the element gets darker and darker and darker, it's getting more and more and more electronegative. By the way, electronegativity is measured on a scale from 0 to 4, and I'm not sure why they chose to do that. It doesn't really have units per se, it's just a relative scale from 0 to 4. And so you'll notice that fluorine is the most electronegative element on the periodic table. And you'll also notice that francium is the least electronegative element on the periodic table. And in general, as you move across the periodic table from the bottom left to the top right, you're going to get more and more electronegative. There are, of course, some exceptions along the way. For instance, it looks like manganese is a little less electronegative than chromium, and zinc is less electronegative than copper. But in general, as you move either up or to the right along the periodic table, you're getting more and more electronegative. Exceptions to this, some really important exceptions, are the noble gases. The noble gases don't have electronegativity values. And that's for a simple reason. They don't form chemical bonds. I hope you remember that noble gases are really, really unreactive. And what that means is they don't lose electrons easily and they don't take electrons easily. Chemical bonding is all about valence electrons, and the noble gases already have a stable arrangement of valence electrons. They have a full octet in their S and P sublevels in their valence shell. And so they're actually really, really stable. They don't form chemical bonds. And so that's why the noble gases don't have electronegativity values. It's not because they equal 0. It's just they don't have electronegativity values. It doesn't make sense to talk about bonding electrons for the noble gases. So we just kind of ignore them. It would be, if you said like, what's helium's electronegativity value? That's just it's kind of like a nonsense question. It's not possible. It's like, how many sides does a circle have or something? It's like it doesn't make sense. Or how fast can your dog fly through the air? It's like it doesn't fly. So the noble gases, what's their electronegativity values? They don't have electronegativity values. Okay, so why is electronegativity important? It turns out that covalent bonding and ionic bonding, whether or not electrons are shared or transferred between two atoms, has everything to do with electronegativity values. In general, metals have very low electronegativities. So the metals on the periodic table if you basically pick any metal here on the periodic table, you'll see that it has an electronegativity value of about 2 or less. So metals tend to be low electronegativity, small electronegativity values, and nonmetals have a high electronegativity. Okay, now there's of course some variety, and metals tend to be less than 2, but there are, if you look at these particular values, they got to measure it out here. Looks like palladium and platinum and rhodium, ruthenium, iridium, osmium. I actually never noticed that. All of those elements right there, they're all really, really expensive, dense metals, and they're also quite electronegative for metals. Gold, silver, mercury, they're all right there about 2, but that's about as high as you get for metals. Nonmetals are much more electronegative. Hydrogen, in fact, is the the least electronegative nonmetal. If you pick any other nonmetal, you'll see that it has, so the nonmetals are above the metalloid line, all right, and so got this, well, the stair step. Normally I draw it in a different spot. Right, that's sort of the stair step with the metalloids and the metals. And I'll cross out the metalloids so we can ignore them. Silicon, germanium, arsenic, antimony, tellurium, polonium, and there is that other period with the newer artificially made elements. It's not on this one. Astatine, perhaps. Everything above that line, and boron is a metalloid as well. It's greater than hydrogen. Phosphorus is actually a tie with hydrogen, but hydrogen is the least electronegative nonmetal. Okay, so let's see what this has to do with the types of bonds that we've learned about. Okay, so we've learned about covalent bonds. That's when atoms share electrons, and it turns out that covalent bonds have something important when we look at their electronegativity values, the electronegativity values of the atoms involved. So let's consider a hydrogen-hydrogen bond. So this is like the Lewis structure for the hydrogen molecule. And this is a purely covalent bond. This is called a nonpolar covalent bond. It's called nonpolar. And what that means is if you could see the electron cloud, if you could zoom in and look and see what those 2 electrons that are being shared are doing, they're going to be shared equally between the 2 atoms. Okay, so to illustrate that, I'm going to write out the symbols of the atoms again. Okay, and remember that whole firefly thing? Electrons are kind of unpredictable, but also predictable at the same time. Okay, so the electrons would probably spend a lot of time in the middle between the 2 atoms and a little bit of time outside. But it would be a really symmetrical electron cloud around this molecule. Hydrogen atoms have the same electronegativity value. Each one of these atoms has the same tendency to draw those bonding electrons toward itself. And so there is no difference in electronegativity values. So there's a 0 difference. Let's go with blue. The difference in electronegativity, that's what this means. Is there a difference? Delta means difference, or sometimes we think delta means change, but to calculate change you do subtraction. Is there a difference? And no, there's not a difference. The electronegativity values here would be 2.1 minus 2.1, the same electronegativity, and so no difference at all. That gives rise to a nonpolar bond. Let's look at the fluorine molecule. Okay, so this is not the full Lewis structure. Of course, there's lone pairs around the fluorine atoms, but I want to focus on that bond. What kind of bond is it? Well, again, if you looked at its electron cloud, you would see that those electrons are being shared equally between the two fluorine atoms. They'd spend the same amount of time around that fluorine atom on the left as the one on the right. Okay, and so this is also a non-polar bond. Now, fluorine is much more electronegative than hydrogen. If you compare the electronegativity value of fluorine, it's 4. Fluorine is the most electronegative element on the periodic table. That's important to remember. It's the most electronegative element on the periodic table. It's at the top right of the periodic table when we exclude the noble gases, which don't have electronegativity values. So fluorine's the most electronegative. And so you might think, well, shouldn't that give a really polar bond? Polarity in a bond has to do with the difference in electronegativity values. So even though a fluorine atom is very electronegative, if it's bonded to another fluorine atom, this is like a tug-of-war match that's a tie. Okay, so it's going to be a non-polar bond. Even though both atoms are drawing those electrons strongly towards themselves, they're doing it in an equal way. So there's still no difference in electronegativity. Okay, so this would be like 4 minus 4, which is still 0. It's a non-polar bond. Okay, so now what's going to happen if hydrogen bonds with fluorine? Well, fluorine is much more electronegative than the hydrogen atom. And so with those 2 electrons right here that are being shared, this is going to give rise to unequal sharing. This is a new scenario that we haven't really talked about so far. This is still sharing, it's still a covalent bond, but the fluorine atom is much more electronegative. And so those 2 electrons end up spending a lot more time around that fluorine atom than around the hydrogen atom. Okay, and like maybe once in a while it'll get around to the opposite side. They'll get around to the opposite side of the hydrogen atom, but they're going to spend a lot more time around the fluorine. Okay, and so we call this a polar covalent bond. This is a polar covalent bond. And I should have said these are nonpolar covalent. If it's nonpolar, it's definitely covalent. So the hydrogen fluorine is a polar covalent bond, and that's because we have a little difference in electronegativity. 4 minus 2.1, that's 1.9. Okay, and when we do difference, it doesn't matter which number we subtract from the other, we just take the absolute value of the difference. So subtract the 2 numbers. If you want to, just subtract the smaller one from the bigger one. What's the difference between those electronegativity values? And so we have a little difference here. It's actually quite large for 2 nonmetals. That's about as big as you could get. But we get a polar covalent bond. Now let me show you a new little symbol that represents what's going on here. Since this is unequal sharing, you start developing a little bit extra negative charge on one end of the molecule and a little extra positive charge on the other end of a molecule. This is not an ionic bond, so you don't have a full negative and a full positive charge, but the fluorine atom is drawing these negatively charged electrons toward itself, and it's almost a F- ion. And so we use a special symbol for a partial charge, and that symbol is a lowercase Greek letter delta, and I put a delta minus on the fluorine. And on the hydrogen over here, I'm going to put a little lowercase delta plus. That denotes partial charges. So not full charges, but partial charges. We're not quite to ionic bonds yet. To get an ionic bond, we need a large difference in electronegativity. And so that's what happens when sodium and fluorine bond. We don't really draw Lewis structures for ionic compounds, but if you wanted to talk about what's going on here with the electron cloud, for those valence electrons, okay, sodium is going to lose its valence electron entirely to the fluorine atom, right? So the fluorine atom will just take those electrons. Again, these are just the valence electrons, those two bonding electrons. And so now we've got full charges, Na plus and F minus. And that's an ionic bond. And how do you get an ionic bond? Well, you need a large difference in electronegativity. So 4 for the fluorine minus 0.9, right? 0.9 for the sodium. And that gives us 3.1. Okay, so I don't want you to worry about the numbers so much, other than for nonpolar covalent, there is no difference in electronegativity values of the bonding atoms. For polar covalent, you get a small difference, which tends to be less than 2, but don't worry about that so much. There's an easier way to know if it's a small difference. And for ionic bonding, you get a large difference. So let me just kind of classify this as large. This is small. And these are, of course, 0, no difference in electronegativity. And those are the 3 types of chemical bonds you need to know about: nonpolar, polar, and ionic. Okay, so how can you know if it's should we consider it a small difference or a large difference in electronegativity? We're going to go with the same rule that we learned a while back. When nonmetals bond, you get covalent bonds. When a metal and a nonmetal bond, you get an ionic bond. And that's because when you have a metal and a nonmetal, you're going to naturally get a large difference in electronegativity because metals have small electronegativities and nonmetals have large electronegativities. So the difference between a large number and a small number is going to be fairly large. You're going to get small differences when you have 2 nonmetals. You might be wondering about the case where a metal bonds with another metal. That's something called an alloy, and it's really a mixture. It's not, you don't have electrons being shared or transferred in the same way. They're kind of all over the place. Alloys make a big sea of electrons that are being shared by all the atoms in the crystal structure. And so in high school chemistry, and even in college chemistry, you don't really learn too much about metallic bonding, although it is talked about a little bit. But we're just focusing on the bonds between nonmetals, which are covalent, either polar or nonpolar, and a metal and a nonmetal, which is going to give you an ionic bond. Okay, so let's do a little practice. We're going to rank the following bonds from least polar to most polar. Okay, so least polar would be nonpolar. So which ones of these up here would be nonpolar? Okay, well, if an element is bonded to itself, it's going to be nonpolar. So I see a hydrogen-hydrogen here and an oxygen-oxygen. Are there any others? No, so those right there would be the least polar, OO and HH. Both of those are nonpolar, completely nonpolar, so 0 differences in electronegativity. Okay, then what's going to be a little bit more polar? Let's use a less than sign. At this point, we can refer to the electronegativity values from this page over here. We'll need hydrogens. Hydrogens is 2.1. Everywhere you see a hydrogen is going to be 2.1, so let's list that. Hydrogen 2.1, 2.1, 2.1. That's all the hydrogens. There's oxygens. I happen to remember oxygen's value. Oxygen is 3.5. 3.5. I remember chlorines, it's 3. You can verify 3. Um, 3. And nitrogens, I think nitrogen's also 3. Yeah. So we've got a tie between nitrogen and chlorine as well. Okay, so that's good to know. Nitrogen is 3. And potassium. Potassium is 0.8. 0.8. So now we can do some subtractions to figure out the differences in electronegativities and rank these bonds. Okay, so right here, I already see another nonpolar bond, chlorine, nitrogen. So that's just as nonpolar as these other two. So let's put it down here. The chlorine-nitrogen bond would be a perfectly symmetrical electron cloud nonpolar. Okay, so then after that, let's do a little bit of subtracting. The difference, I'm going to do my subtractions down here. The HCl, 0.9, the difference in electronegativities. Make a little table. Delta ENs. So we've got 3 minus 2.1, that's 0.9. That's its measure of polarity. What else? HO. The HO bond, 3.5 minus 2.1, that's 1.4. The OCl, 3.5 minus 3 is 0.5. And the HN and the KCl. Oop, I'm reaching the end of my tablet, sorry. Gotta scoot this over a little bit more. Okay, so the HN is also 0.9. And the KCl is going to be 2.2. Okay, so now we have enough information to rank these. The 0.5 comes next, so that's OCl. The OCl bond is next in polarity, okay? And then we've got these 0.9s, which are a tie, so the HCl and the HN. And that's because, remember, chlorine and nitrogen have the same electronegativity value, so when they bond to hydrogen, you get equally polar bonds. And then HO, ooh, that was supposed to be a less than sign. And then the KCl. Okay. And which ones of these would be non-polar? The ones with 0 difference in electronegativity. So all of these right here are non-polar bonds. Non-polar covalent. These ones right here would be polar covalent because they have relatively small differences in electronegativity. So partial charges, not full charges. And this one right here, that's ionic. The most polar would be ionic, full negative and positive charges. So I hope after watching this video you understand the concept of electronegativity and why it's important in determining the types of bonds that occur between various types of elements.